When a Boeing 787 lifts off the runway, you are trusting a structure weighing nearly 500,000 pounds to float on thin air. We look at a machine like this and assume it is an absolute, unyielding, solid object. But in flight, it is highly flexible. As the heavy fuselage pulls down and the upward lift pushes back, the entire wing is subjected to massive transverse forces, causing the physical structure to bend. If we look under the smooth aluminum skin, we find a semi-monocoque design, a hollow framework of webs and ribs that actually bears those flight loads. It is here, inside this specific framework, that bending creates a hidden structural threat. A bending beam hides a secondary struggle. Its internal layers are trying to slide apart horizontally. Think about pressing down on a loose deck of cards. The cards don't bend as a single unit. The individual layers slip past one another. The exact same physics apply to solid metal. A beam only functions as a solid object because the material generates an internal glue, a specific friction resisting this horizontal slip. Without that friction, every load-bearing beam in the world would instantly shear apart and collapse. To see how that internal glue actually works, we have to scale down into the material itself, isolating a microscopic cross-section of the beam to trace the atomic-level forces. When a beam bends, the curvature creates an imbalance. The bending moment on one side of this microscopic segment is slightly different from the other. This means one side pulls slightly harder in tension than the opposite side. The laws of physics dictate that an object with unequal forces applied to it must move. To stop this microsegment from accelerating and tearing the metal apart, a horizontal force engages along the plane to perfectly cancel out the imbalance. Engineers calculate this horizontal friction using the basic shear stress formula. They take the applied shear force, V, multiply it by the first moment of area, Q, and divide by the moment of inertia and the width of the beam. This defines exactly how much horizontal stress is required to keep the material intact. But solving this one problem simply creates another. Applying a horizontal friction force along the top and bottom of a microscopic cube creates a couple, a rotational force that threatens to spin the element entirely out of control. A structure can't hold a load if its atoms are spinning. To maintain rotational equilibrium, vertical shear forces instantly materialize on the perpendicular faces, locking the block firmly in place. This is known as complementary shear. Because these vertical forces exist solely to balance out the rotation, the horizontal and vertical shear stresses at any point in the material are mathematically identical. When an engineer calculates the vertical shear stress pushing down through a bridge support, they are actually measuring a forced byproduct. That vertical force exists entirely because microscopic horizontal imbalances are fighting to keep the beam together. This diagram shows a standard rectangular beam overlaid with a glowing heat map of that shear stress. Looking at the distribution, the stress is absolutely not uniform across the material. The upper and lower surfaces of the beam are essentially lazy. Because there are no external surface forces acting on the very top or bottom edge, the shear stress in these areas falls completely to zero. Conversely, the dead center of the beam, the neutral axis, is doing all the heavy lifting. The shear stress peaks right in the middle, hitting exactly 1.5 times the average stress of the entire section. If you were building a skyscraper, paying for steel that does no work is a waste of money. By carving away unstressed material at the outer corners and keeping only what is mathematically necessary, we are left with the highly efficient, thin-walled I-beam. This technical diagram reveals how the stress distributes in this new geometry. The intense vertical shear component is forced to flow directly down that incredibly narrow center web. In this chart, we see what engineers call shear flow. Because the variation is continuous, the stress acts almost like a fluid. The force flows inward from the horizontal flanges, symmetrically merging and pouring down the central web. Because of this sculpted shape, the central piece of an I-beam is remarkably efficient, carrying up to 98% of the total applied shear force. These stacked steel I-beams are the physical result of the mathematical equilibrium required to resist those internal forces. This delicate internal balance holds our engineered world together. But this perfection assumes the load hits the beam exactly on center. If a force lands even slightly off-axis, it introduces a tearing torsion. Finding the single point that can stop that twist requires locating the elusive shear center.